Okay. Okay, so this is a sort of very simple regression pipeline. So we will learn regression using this model. So the idea is that there is a power plant, and it has various measurements. And what we are interested in is being able to do predictions for the power output based on various environmental variables. So in this notebook, we will do steps 1 through 4. So state our business understanding of the problem, load our data, explore our data, and visualize our data. Then we'll do data prep and modeling. And finally, we'll do tuning and evaluation and deployment. So you guys already know Spark Streaming, so we'll use Spark Streaming for deployment. Deployment just means once you've learned your model, queries are coming at you in real time, near real time, and you have to serve your predictions back to the client. Right? So these sort of the full ML pipeline. So we're trying to predict power output given a set of readings from various sensors in a gas-fired power plant. And of course, this is a very complex process. I've had a PhD student who's worked on neural network-based controllers for gas turbines off of the Iranian coast. This is in New Zealand. And so it's a pretty non-trivial task, especially for old gas turbines. So the ML task we're going to do is regression, because now the label or our target we're trying to predict is a continuous numerical value, right? So floating point numbers, right? And this is to be contrasted with classification problem like spam or not spam or digits 0 through 9. Okay, so please knock yourself out on this programming guide. And I just want to point out there's quite a lot here. ML libs, so there's 2 ML libs. One based on RDD, another based on data frames. So we'll use either or. As you can see, there's quite a lot. There is linear models. There's even some generalized linear models in this framework. Support vector machines, naive Bayes, decision trees. Later today, I really want to get to ensembles of trees. So we saw random forests last time. Remember, just one decision tree. Sorry, just decision tree. But now we're going to have an ensemble of them. And then we'll have a forest of these decision trees. And specifically, we'll look at gradient boosted trees. Right? And even in this power plant pipeline, I believe we will let models built using random forests fight for predictive power with a linear regression model. So you can have different families of models actually sort of fight it out. Right? Anyway. So there's quite a lot of stuff here. So this particular data comes from the UC machine learning repository, combined cycle power plant. So you can kind of get a look into this. It's kind of an overused data set in a way, but that's okay. Just like the handwritten digits. So here is this peaking power plant actually. Yeah, it's in New Jersey. How many of you have been to New Jersey? So you know about jug handles. This is the weird way the small roads connect to the big roads in New Jersey. Anyway, my wife is from New Jersey. So yeah, this is basically the machine learning repository from UC Irvine, and here is a brief explanation of this data set. It's about 9568 data points over 6 years, and I think it tells you about the various features, so that there's temperature in the range negative 1.8 Celsius to 37.11, ambient pressure is AP, and relative humidity, exhaust vacuum, and net hourly electrical energy output. And that's kind of what we're going to predict using label data, historical data. Right, and this is also the average taken from various sensors. And okay. So yeah, you shouldn't worry about this. So I'm going to try and attach it to this guy. So this is our first step in any of these data science process tasks, is to understand what your clients want. So we're trying to predict power given the set of readings from various sensors. So we're going to attack it using the simplest regression first, linear regression. Okay, so so this data should already be there for you. So if you Control Enter, you should start seeing these sheet1.tsv, sheet2.tsv. Do you see that? It's already in your Databricks datasets. Okay, good. Otherwise, it's a lot of work. It's not a lot of work. It takes a lot of time. So this should be there, and then but if that's not there, then there is also instructions below on how to load it. Okay, so once your cluster, well, my cluster is still processing. So if you just hit this, Control Enter this, you're going to just read these. This particular tab separated variable is TSV file, sheet1, right? And that should load up the file for you, and then you can just take the first 5 elements and print each line. So this is kind of our basic data set. So temperature, pressure, relative humidity, exhaust vacuum, and power output. Okay, so I guess I'm saying I need 2.2.0, which is what I've started. So then the next thing we're going to do is simply use this Spark dot read method, and we can just say dot format CSV option header is true. Remember, the first line was all this header information. So we want to do that, and we want to infer the schema automatically. When we say option infer schema true, it'll try to figure out the data type automatically from the formatting. And then we say the delimiter is the tab character, because this is tab separated variable file, and it's already a pre-clean data set, so we don't have to worry about regex or anything like that. So this is going to give me the same exact sheet1, but as a data frame. So then we can just see the schema. So you see that we have the schema of these variables, and it's already inferred these to be doubles. Okay. So if you do dot count, you should see 9,568. So 2.1 is an alternative thing. So this is how to load data using the GUI feature in Databricks. So this is a useful thing. So you just have to basically hit this data button, and then you'll go to this table menu, and then you can start doing this plus and adding files, and essentially doing the same thing in a GUI way. So I've sort of explained this in pictures here. So it'll load all those files, and you can choose choose the actual types here by if you want this to be, for example, if there is not decimal numbers and you want it to be not read as an int but as a double, then you can specify it in the GUI this way. Okay, so you can review the schema and create a table. That's Regression. So the next step is to explore your data. Oh my god, this is taking a long time. Explore your data. So here we are going to use the dot show method first. And I haven't, dropped you guys down into Spark shell. So let's see. So this is kind of important. So, if you go to the, so this is kind of a slight Apache Spark. Yeah, so if you go here and, you can actually download the, whatever version of Spark you want. I'll just take Hadoop 2.7, and then you can just download it. It'll tell you the one specifically for your operating system. Once you download it, then you can basically push D is a nice command, so you can come back here. So Spark. So let's see, I go Spark 2.
Close that light.
Yeah, it's a good idea. Try some random stuff. So you see, once you download it, you'll and unzip it, you will see a directory like this. So then, and inside the bin for binary files, you'll see all of this stuff. So if I do bin Spark shell, so this is how I would execute Spark in my own local environment. And so this is kind of how I learned Apache Spark, right? It's the same thing. In fact, the Zeppelin notebook is just another layer, tiny layer on top of Spark shell. So of course it'll give you lots of warnings, and so you can do sc.parallelize seq of say 1, 2, 3. Let's call this something. All right. So that's created a RDD, right? So I can do a.count. Okay, you get the idea. It's not going to have all the super GUI things, but so you do want to, you do want to know about this at some point. So yeah, and also maybe by the time the course is over, we'll have all the same content in Zeppelin and Jupiter as well, which are open notebook formats you can use from your own computer. But Databricks is convenient for now. Okay, so now let me quickly run the cells I think I need. I don't need all of this. So that's my power plant RDD, and that, and my Spark power plant data frame. Let's make sure that's good. Okay, so I think I've caught up. So we can show 10 elements. So of course, in Databricks and with the slightly extra code on Zeppelin, you can use this display function and immediately see the scatter plot. So we did this already for the song 1 million song example. So now I'm looking at all pairwise scatter of these 5 variables, right? So so PE is what I want to predict eventually, and I want to use these environmental and whatever the machine features. Okay, so by staring at it, you can see that the power output is decreasing kind of linearly with temperature. So I'm not sure what that means exactly. So as the temperature increases, the power output is decreasing, right? I mean, same with vacuum. So the exhaust vacuum, the higher the exhaust vacuum, the lower the power output. But these are sort of more smeared out. As atmospheric pressure increases, the power output kind of increases, and I don't know, this is a bit more blotchy. And of course, you see there are other kind of correlations, both positive and negative correlations. You can kind of ignore this half because it's just the same stuff upstairs flipped around. But there are somewhat more complex dependencies between vacuum and pressure and so on, relative humidity and exhaust vacuum. Okay, that's kind of the raw data. And then, of course, the diagonals is always the sort of kernel density estimated histogram or kernel density estimate of each variable. So they're kind of unimodal. This one's kind of interesting, but so oh, by the way, Marina was wondering, so you can always turn this into a table format by hitting that table button, and then you can download, so you can download full results. If you download full results, it'll ask you to re-execute the command. But if you just hit download, it'll just grab the first 1,000. So that's how you can get CSV. That's how, for example, Olaf grabbed my Twitter history to put it into his D3 thing. Okay, so you can save it locally this way. Okay, so oh boy. Okay, so we are now going to play with SQL a little bit. So we can ask, what are the tables in my SQL context? There's nothing there. So then we can see what's in my catalog. There is nothing. And okay, so that's where my databases live. So then I'm going to create or replace temp view. So I'm going to create this sort of temporary view of this power plant data frame into a table called power_plant_table. So this is so that I can do SQL queries and also be able to call the same table from different languages if I want. Okay, so yeah, so anyway, these are just some utries. So SQL context is quite powerful. So if you put a dot and hit tab, there's quite a lot you can do. So all of this is in the docs for you to read later. It's kind of how I mostly figure out syntax. Yeah. So you can always remove the table by using drop temp table command if you want to. Okay, but let's keep it there because we want to do these. So we can drop into SQL and just do the same exact thing. Select star from power plant table. This is just mostly a review of the first day. Okay, and I can ask it to describe, which is just telling you the schema basically. Yeah. So let's do some basic statistical analysis. So if I take a data frame and do a dot describe method on it, it'll give me the count of each variable, the mean, the standard deviation, the minimum, and the maximum. These are good things to look at, just to get some rough idea of the bounding boxes and the mean and the standard deviations. So everything looks good. All these numbers are the same. And if they're not the same, then maybe we'll have to go in and do some cleaning. So now let's visualize our data using just pure SQL. So I'm just doing select atmospheric AT, which is the column name, as temperature, and PE as power from the, this is very convenient. So then we can look at pairwise plots, right? So as I said, there is a very nice negative correlation between temperature and power. So I don't know, maybe they're using this to heat up homes. I have no idea. So similarly, you can do the same between V and exhaust vacuum. So this linear correlation is just this really dangerous word, right? So it's a massive many-to-one mapping from points in 2 dimensions to one number. So when you have that means lots of different patterns of points in 2D can give you the same exact number called correlation, linear correlation, and you've got to be careful. So I don't know if I do this, but if you look for linear correlation, do people donate to Wikipedia? I don't know. It's a good idea. I think there is isn't there a plot here? Oh yeah, there it is. You see, look at these patterns, right? So this is like the straight line everyone talks about. Correlation 1. It's almost like a slope 1. But you know, as it gets more and more smeared this way, it decreases. And then as it tilts around, it becomes negative. So this is kind of what a lot of people think about when they say linear correlation, the perfect thing. But you know, there is these patterns are also 1. It's kind of dangerous, right? And this is 0, you know. So okay, so again, these are crazy, right? This is 0. The middle one is undefined. This one. Okay, fair enough. Well, it's probably positive a tiny bit, no? Oh, you checked the system? Oh, okay, cool. Yeah. Yeah, he's a pure math guy, you know, I should trust him. So, I haven't checked it. So anyway, I mean, but it's still valuable, okay? So, I mean, I'm mainly trying to show that each of these patterns are telling us, you know, different patterns, and let's see what we can do, right? So anyway, as I said, I generally shy away from SQL just because it's going to bite us later. So, but feel free to, yeah, play with SQL if you want. So I'm just doing the same thing this way. So I think, yeah, that's mainly what I wanted to show here in this one. And these are the links to the original papers. So we'll come back to how to model this data after we have a crash introduction to sort of linear algebra. This is a really, you know, mixed audience, so some of you may probably want to go to sleep for a little bit. But I also need to introduce linear algebra because, and also I really should apologize. So the original plan for the course, I was going to do the foundations first, like any normal course, the 3-day foundations, and then everything was going to build after that. But because of the schedules of the various domain experts, I couldn't get it to work like that. So it's a bit schizophrenic. So here again, I sort of expect you to be able to drop into Amit's CS 190.1x, the Scalable ML course. So I'm mainly embedding key ideas from his course, but also his course is on Python, so this is a Scalarification of it. So in Scala, the main library is called Breeze for linear algebra, so we'll kind of get our hands dirty with Breeze. So yeah, so this one's a really good quick start on Breeze. And I think I'm just basically pulling bits and bobs from there. So this is actually, yeah. So we'll do it in Databricks directly. So we'll provide a review of basic linear algebra concepts that will recur throughout. So it's basically vectors, matrices, arithmetic operations with vectors and matrices. And then we'll get into sort of local single machine arithmetic, and then later on we'll get into distributed linear algebra, the next notebook. That's like multi-machine linear algebra. Okay, so what is a quick visual geometric interpretation for vectors, matrices, and matrix vector multiplications? How do you intuitively understand eigensystems with real and complex eigenvalues and just low dimensions, right? So this is all like super quick 200 level recall. Okay, so this one is quite good. So let's get into this. It's still there. Otherwise, I'll draw on the board. Okay, so eigenvectors and eigenvalues. So why are they very important? Because a lot of the problems John talked about today, we'll see if I succeed tomorrow. My mission is to show you guys a large class of those problems are actually very elegant and simple problems from early 1950s non-parametric inference for Markov chains by this guy called Billingsley. So they can be recast in them. And the way you can recast it is, once you understand what Markov chains are, you can take the OpenStreetMap and break it into small segments, you know, roads, and you know which road connects to which road. So that tells you, where you can go. So each road segment can become a state in your Markov chain. And you can think of a Markov chain as some kind of a, say, frog jumping between lily pads, and each lily pad is like a state. And of course, the frog cannot like superhuman jump, right? Super frog jump. So it'll just go to some neighboring states. That's called the neighborhood of that state. So and then it'll choose which lily pad it jumps to with some probability. And the probabilities, let's say, imagine is given by some kind of, you know, what do you call it? Polygonal cylindrical die that sits in each lily pad. So the frog rolls the die. So if there are only 3 lily pads you can reach, it'll be a Toblerone, like a pyramid, and it'll be loaded, right? So it'll roll it, and whatever face comes on the bottom, it'll look at it and then jump to that lily pad, right? This is basically a Markov chain, right? It just keeps jumping, and so there are many quantities of interest, and of course we'll study Markov chains very carefully in the second week of the Foundations course. But one of the most important quantities is if the frog kept doing this forever, and every time it reaches a lily pad, let's say there is a counter, it checks, like cha-ching. So this counter keeps track of its visits. Then after, you know, a million years, you go there and then you take all the visits and divide by the total number of visits. That tells you what's the relative frequency with which this frog is to be found in this lily pad. That means, you know, if I just come from another dimension like a superhero and say, I want to predict the probability the frog will be in a given lily pad, then I can use this relative frequency. So that's called the stationary distribution of a Markov chain, and it's a very, very basic quantity. It doesn't exist all the time for Markov chains, but it under certain conditions, it's guaranteed to exist and to be unique. And for a lot of problems John was posing this morning, they can be recast as stationary distributions of certain projections of OpenStreetMaps, where now the OpenStreetMap segments could be the states that the frog jumps. And of course, the frog is the cell phone trajectories of lots of people. So now there's not one frog, there's multiple frogs. So this is multiple frogs jumping, right? But it's a cartoon, but it's good enough because it'll immediately get you things like what is the most traffic-heavy segment of the road, and there are, you know, easily we can add bells and whistles like make this a time-varying Markov chain. So there is a sort of time dependence on the jumping behavior and all of this type of stuff. Yeah, and also like a lot of the other problems, because tomorrow I'll focus mostly on arithmetic and operations using Magellan. But then with these modeling capabilities, you can answer questions like co-occurrence. Remember, he was interested in understanding segregation patterns from cell phone trajectories. Then the sort of co-occurrence of different people who sleep in different neighborhoods in space-time is actually, again, can be recast as a Markov chain problem. It's a bit more subtle because you have to understand the maximum likelihood theory for Markov chains and all of this, but it's, again, the same machinery can be used. Okay, so let's get into eigenvectors and eigenvalues come there because when eigenvalue is 1 for this matrix representation of a Markov chain, then that gives you the stationary probabilities basically analytically. Right, and also remember Google's PageRank algorithm. This is the algorithm that made Larry Page and Sergey like superheroes, right? Literally Stanford PhD students. That's a Markov chain, right? And their mathematical, you know, this is old mathematical algorithm, but what they did was, of course, engineering, amazing engineering. But what they did was this. So there, each lily pad is a website, is a site. And then it's a, you know, you can sometimes go into a site but never get out because the links are directional. So, you know, it's a directed path. But then if you just take the World Wide Web as it is, you will never reach stationary distribution because you can get trapped into sites that nobody else cites, you know, nobody else links to, right? So what they did is they said, okay, I'm going to have a random surfer model. So the original thing is something like there is like an oracle that, you know, flips a coin with probability heads of coming up. It comes up heads with probability 0.85. And it comes up tails with probability 0.15. So if it comes up tails, then the random surfer will choose one of the existing states, websites at random, uniformly at random, and just hops there, right? So this random surfer will never get trapped with probability 1.5. It will always jump to somewhere. And then with the remaining probability 0.85, he'll choose one of the out neighbors of wherever he is, right? So then of course he'll choose that uniformly at random. If there are 80 links, pointing to out from a site, then he'll choose with probability 1/80 one of the outgoing links. That's basically PageRank's most primitive version. Right? So let's see. So here is a vector v. So we represent a vector v like this, right? It's 2 and 3. So we put a column vector, and so I think we can move this. Used to be able to move. See the numbers change. So these are just an XY coordinates. So I usually imagine the vector v as an arrow going from here to that point, right? And then now A1 and A2 are column vectors. So the green one is this one, A2, and the blue one is this one. So I can sort of I can change this so it changes, right? So you can think of a matrix as a bunch of column vectors. This is one visual embedding of a matrix, but it's a natural one. Then this operation A multiplied by V is, so you're right multiplying A by the vector V. That means multiplying from the right. So Eric, laughing now. Anyways, it's for Eva. I want Eva to be brave, So A is like a bunch of numbers, right? So then V is a bunch of numbers, right? So let's say I forgot notation. Let's say this is A11, A12, A21, A22. So when I do multiplication, I just draw like this. So then I'm taking A11 times V1, right? And then I'm taking A12 times V2, and that becomes the first entry of my of whatever comes out, this new vector that I'm cooking, right? And then the same way I use the same thing to this. So this will be A21 times V1 plus A22 times V2, right? So there's also like another natural way to think about it. You can think of, so you can think of, because you're hitting both of them with V1, when you take any vector and multiply it by a scalar, by a number, then V1, if it's just 1, it leaves this guy alone, right? Multiplying by 1 doesn't change anything. Let's say this is 2, then it stretches it, right? So if it's negative, it flips it. And if it's 0, it just kills it, basically. So you can think of this operation as, essentially we take weight V1 and stretch this guy, and take weight V2 and stretch this guy. So basically, if we have A1 and A2, and say V1 is 2, then we stretch this by 2, and say V2 is half, we stretch this by half. So this becomes my stretch thingies. And then I'm just adding them, right? These weight stretch things I'm adding. So what happens when you add I don't know, you guys know this, right? This is the parallelogram. Or the picture. So you have the diagonal of the parallelogram is the sum of the vectors, right? So that's what this is. So this coordinate and this coordinate of this stretch thing is just this and this, right? So am I doing, yeah. That's what that is. So you basically, and that's what we're showing here, basically, right? Yeah. So you see, yeah. Okay, that's basically vector multiplication by a scalar and matrix multiplication by a vector. Okay. So now what is an eigenvalue? So imagine this case where this A times V we did, right? This is the A and this is the V. And suppose we can factor out this common number 5 out, right? So, this was 5 and 10. We pulled 5 out. That means we can write this as lambda times v. So lambda is 5 here. And so here, lambda is now going to be called an eigenvalue of this eigenvector v, eigenvalue of this matrix A for this eigenvector v. So all that means is, I can have situations where when I do a matrix multiplication, whatever comes out simply is going to be the same as v. So remember, 1, 2 was v. V is still there. And all it amounts to is stretching v by 5, right? So that's the special thing. So we can kind of reinterpret what comes out as a multiplication of what went in. That's eigenvalues and eigenvectors, basically. Okay. I don't know what this is about. Oh yeah, so now, so we changed the columns of A and drag V to be an eigenvector. So every point on the same line as an eigenvector is an eigenvector. So that means, if I multiply this V by some constant, say 24, so then I'll have 24, 48, and 24, 48, the 5 will still be there, the eigenvalue. So that means on the same direction as V, every vector along that is still an eigenvector. And then we can have more than one eigenvector and eigenvalue, right? So now, when you just have one eigenvector, I told you every vector along that line forms an eigenspace. All those eigenvectors form an eigenspace. Then if we have two vectors with different eigenvalues, then any linear combination of vectors between these two eigenvectors will also form an eigenspace. So I think that's kind of what these guys are trying to say here. Okay, what are eigenvectors good for? What is it good for? It's an applied course. Otherwise, we won't listen. So anyway, so eigenvalues and eigenvectors are good for many things. In particular, when we are interested in keeping on multiplying V by a matrix A in this way. So we have V initially, and then we have A times V, and then A squared times V, and so on. And there's like a whole business model in mathematics called dynamical systems. Sorry, that was a joke. So that's what these guys study, This is a simplification, of course, what they study, but they try to figure out what happens to V if they keep doing the same thing again and again to it. No, this is a very elegant and very complex subject of mathematics, right? This is not just matrices, right? I mean, they complicate the spaces and everything. But see, now the beauty is this, and this is completely natural, right? So what is this A squared thing got to do with Markov chains? So in Markov chains, what we have, let's make a little Markov chain for A. So usually in Markov chain literature, instead of calling it A, you call it P, right? So you have, say, two states. I don't know, I'm going to call the states 1 and 2. So this is lily pad 1, lily pad 2, or whatever. And then, so this will be P11, this will be P12, and this will be P21 and P22. So these are the probabilities, this is essentially the, if the frog sits in one lily pad, it's only connected to another one. This is the probability that it chooses to remain where it is. Okay, it flips it once it lands there. And then this is the probability it decides to go from state 1 to state 2. So this could be half-half or quarter. And of course, these have to sum to 1. So because this is it's called a stochastic matrix or transition probability matrix. So transition probability matrix, what are the conditions? The Pij's should be greater than or equal to 0. And the sum of the, I'm just going to, basically the rows have to sum to 1. So in this case, P11 plus P12 should equal 1 exactly, and P21 plus P22 should equal 1, right? Because with certainty, it'll go somewhere. It'll either stay where it is or somewhere else. That's basically, and of course, if you have a million states, it's the same rules, right? So PageRank is basically the same thing, right? Yeah. So then what I'm saying here is, so if I take P squared, what is p squared? So I take two matrices, p multiplied by p. So to multiply a matrix by itself, I again do the same thing. So I'll have, you know, 4 numbers, right? So I can do the same rule. So to create the first entry of the new matrix, right? So if this is 2 by 2 and this is 2 by 2, 2 rows, 2 columns, then, you know, you have to always make sure these are exact, and then you just throw this, so you'll get out at 2 by 2. So once again, I take these entries and multiply them by, you know, I do the same dot product operation on that. So I'll get, you know, P11 times P11 plus P12 times P21, right? And what that means is this new entry is the probability of going from state 1 to state 1 in 2 steps, right? So that's what basically that is saying, right? So I either stay at 1 and stay at 1, or I stay at 1 and no, then yeah, I go to 2 and come back to 1. Sorry. So it takes care of all of that. And what is the connection to all of these Markov chain theory and graphs is the most important point. So linear algebra and graph theory are kind of not really that different from one another in many ways. So there's a whole theory called Markov theory that combines the two, which I don't know too much about. But you can also derive the stationary distribution of a Markov chain using just graph methods, you know, graph programming methods, and that's what we'll do hopefully at the end of today. So what is being shown here is I have my V. V is now going to be my, in the Markov chain context, V will be my state probability. So V will be, say I initially started at 1, state 1. So that means this becomes my state probability vector. Suppose you found the frog in the lily pad named 1, right? So with probability 1, it's in that state. And with probability 0, it's definitely not in the other lily pad. So this is how you would initialize it. And then you would multiply this by p, right? So how do I do this? Oh yeah, I did it like a physicist way. Well, let's do the physicist way. So you do pv, right? So in probability you do this. So you would do the row vector 1, 0, it doesn't matter. So we'll stick to this. So then this will tell you what is the probability I will be at state 1 or at state 2 in one time step, right? And p square v will tell me, you know, having started in state 1, where will I be in 2 time steps and so on, but in a probabilistic way. These are called, what are they called? State probability vectors, I think. So of course, the question I said is if the frog keeps jumping forever or the random surfer in Google's PageRank keeps surfing forever, what will happen is basically what's given by this. So we start at some initial configuration and then we hit it with a square, a cube, and so on. And what you start seeing is that it's going to converge somewhere, right? It's going to converge to a point, and that's essentially the stationary distribution for a Markov chain if the eigenvalue is 1, okay? Because the matrix is constrained. All right, I won't get into these other things like Fibonacci numbers. So there's a whole world of discrete dynamical systems and so on. Yeah, these guys are just explaining the steady state thing I was telling you about. Yeah. So you can do a lot of modeling using just these simple ideas. Complex eigenvalues are more interesting. So how many of you understand complex multiplication? Yeah, I believe you guys. Yeah, okay, good. So anyway, let's look at the picture. It took me a very long time to understand. I only understood it in grad school, like 3rd year. Really understand. But anyway, I'm slow. So so you know, here is basically where you start now. So now you're allowing the number systems to not just be real numbers on the line, but also this thing, you know, there's another axis called the imaginary axis, which allows for the definition of square root of half, and it sort of formalizes multiplication by -1 as a 180-degree flip, and the square root of -1 becomes a half turn, and blah blah blah. But you can have much more complex systems like this, right? So you can start from here. You can have some, interesting spirals and start seeing what happens, after many iterations. Anyway, we won't need anything with complex arithmetic here. Ooh, what is this? Uppsala men, don't watch this video around your wife. Oh my god. I don't know what's going on because I put my Gmail. I should show you guys, like, just for fun. What? I don't know, like, what's going on. So I have all these crazy people demanding that I do strange things with them. I have no idea. It all goes to my spam, but I think it's because of the Meetup, because I put my Gmail on the Meetup, and things have been crazy since I did that. Anyway, I probably don't recommend you put your actual email address on Meetup. People are not just meeting up for big data. Anyway, that's all right. That's just like to jog people's memory, and those who don't have formal linear algebra, not to feel afraid. It's just some maths. So let's watch this very briefly. I kind of wanted to, get some Amit in.
In this segment, we'll provide a review of basic linear algebra.
Sorry, I forgot to plug in the. Is the sound?
A matrix is a two-dimensional array, and we'll denote matrices via bold uppercase letters. For instance, the matrix that you see in the slide is denoted with a capital and bold A. A sub ij denotes the entry in the ith row and jth column of the matrix. So for instance, the first entry, the top left entry, is denoted as A11, and the entry in the third row and second column is denoted as A32. We say that a matrix with n rows and m columns is an n by m matrix. So for instance, the matrix in our example here, having 4 rows and 3 columns, is a 4 by 3 matrix. If a matrix is n by m, we also say that A is an R to the n times n. And we'll use these two notations interchangeably throughout the course. Next, let's talk about vectors. A vector is a matrix with many rows and 1 column. We'll denote a vector by bold lowercase letters. So for instance, the vector in the slide is denoted with a lowercase bold a. A sub I denotes the ith entry of a vector. So for instance, A sub 2 denotes the second entry of the vector. If a vector is n-dimensional, then we say that A is an R to the n. In our example in the slide, A has 4 dimensions. So A is an R to the 4. Next, let's talk about the transpose operation. In a transpose, we swap the rows and columns of the matrix. So for instance, imagine this input matrix here. Its transpose looks as follows. And as you can see, the first row on the left, 1, 4, becomes the first column of the matrix on the right. We can do something similar in the context of vectors as well. Let's talk about 2 different properties of matrix transposes. The first is that Aij, so that ij entry of A, equals the jith entry of its transpose. And we see this as follows. So A12 equals 4, and similarly, A transpose 21 equals 4. Second, if A is n times n, then A transpose is m times n. And so, for example, in the matrix examples here, the 3 by 2 matrix, when transposed, becomes a 2 by 3 matrix. And similarly, the 3 by 1 vector becomes a 1 by 3 vector. And both of these properties follow directly from the definition of a transpose. Next, let's talk about addition and subtraction of matrices and vectors. And these are element-wise operations. So for example, adding these 2 by 2 matrices, the first entry just equals 3 plus 4, which corresponds to the first entries in each of these matrices. The second one is 6 plus 8, and so on. Subtraction is the same, and here in the context of 2 vectors, to get the first entry, we just subtract 5 minus 4, and to get the second entry, we subtract 1 minus 3. It's important to note that matrices must have the same dimensions when performing addition and subtraction. So this following vector subtraction is perfectly appropriate because both vectors are two-dimensional. Similar, these two matrices are both 2 by 3, and therefore it's possible to perform the addition. In contrast, in this third example, the matrix on the left is 2 by 3, whereas the second matrix is 2 by 2, and therefore this matrix addition is not possible. Next, let's talk about matrix scalar multiplication. And here, the idea is that we want to multiply each matrix element by a scalar value. So for example, here, we're multiplying each entry in this matrix by the scalar value 3. So the first entry becomes 9, the second one becomes 18, and so on. We can do the same thing with a vector and with a negative number, as follows. Now let's talk about scalar products. And this is a function that maps two vectors to a scalar. So for instance, if we take as input these two three-dimensional vectors, the output, or the scalar product of these two three-dimensional vectors equals -9. How do we get these numbers? Well, to do so, we perform pairwise multiplication on the vector elements. So we first multiply their first entries, we then multiply their second entries, we then multiply their third entries, and we take the sum of these products, and we get -9. It's important to note that these two vectors must be of the same dimension, and also a scalar product is also called a dot product or an inner product, and we'll use this terminology interchangeably. More formally, matrix vector multiplication can be defined as follows. We start with a matrix A, and we want to multiply it by a vector W, and we get a result Y, which is also a vector. So how does this work? Well, consider the ith row of A, as well as the vector W. Then we can define Yi, the output, as the scalar product between the ith row of A and the vector W. Moreover, we'll perform this operation for each row of A. So if A has n rows, then Y is an n by 1 vector. Additionally, to perform a scalar product, remember that the two vectors have to have the same dimension. So the number of columns of A must equal the number of rows of W. Now that we've defined matrix vector products, we can revisit or reinterpret the scalar product as a special case of a matrix vector multiplication. In particular, recall that we assume that vectors are always in column form, so that an m-dimensional vector can be represented as having many rows in one column, or that it's an m by 1 vector. And again, since scalar products require two matrices that are of the same dimension, x, if we're taking the scalar product between W and x, we also know that x is an m by 1 matrix, and therefore x transpose is a 1 by m matrix. And so as a result, we can think of a scalar product simply as the matrix as a product of x transpose W. And the output is Y, which is a scalar product, which is a scalar. Next, let's consider matrix-matrix multiplication. This also involves several scalar products. And so let's start with an example. So here, we first take the first row of the matrix on the left and the first column of the matrix on the right, and we take its scalar product, equals 28, and that gives us the first component of our resulting matrix. We then do the same thing with the second row of the matrix on the right, and that gives us the top right entry of our resulting matrix. If we then continue this process, we get the full result. So more generally, how does this work? Well, matrix-matrix multiplication involves two matrices, A times B, that we're multiplying by each other, and it returns the resulting matrix C. And so first consider the ith row of A and the jth column of B. Then Cij equals the scalar product of the ith row of A and the jth column of B. We'll repeat this process for each row of A. So if A has n rows, then so does C. And so that defines the number of rows of C. Next, as before, to perform an inner product, we must have matching dimensions. Therefore, the number of columns of A must equal the number of rows of B. And finally, we'll repeat this process for each column of B. So if B has P columns, then so does C. So in summary, matrix-matrix multiplication involves multiplying an n by n matrix by an m by p matrix and returning an n by p resulting matrix, where each entry of that resulting matrix is generated via a scalar product.
Okay, so I'm sort of playing this 11-minute video because it's basically a crash course on linear algebra in 11 minutes. But what it really nicely plugs to later on We may not have time to see the videos, but to fully understand what's happening with distributed linear algebra, that means the matrices are so big it won't fit in one machine anymore, right? So these very specific, what exactly is M? Can M be represented by within the range of the longest possible int? So if that's the case, then these are called, N can be very large, N can be like, I don't know, billions and billions of rows. But if M is like, size of an int, not long int, then it's called a tall and skinny matrix. So then a lot of these operations can be shipped and done locally on each node, because you see the actual dot product operations will fit into each machine. So later on, Amit gets into all these details, and in fact, I'll kind of give you guys like a whirlwind tour, but feel free to drop into the other videos that I just have linked. We won't have time to watch now.
Next, let's note two properties of matrix-matrix multiplication. The first being that it's an associative operation, or in other words, A times B quantity C equals A times quantity BC. However, it's not commutative, or in other words, in general, AB does not typically equal B times A. Now that we've defined matrix-matrix multiplication, we can introduce the notion of an outer product, which is another operation that takes as input two vectors, just like the scalar product, yet unlike the scalar product, which returns a scalar, the outer product returns a matrix. And the outer product can be viewed simply as matrix-matrix multiplication, where Cij, the ijth entry of the resulting matrix, is simply the product of the ith entry of X and the jth entry of W. Next, let's define the identity matrix. And to do so, let's think about what happens in a scalar setting. In the scalar setting, the number 1 is the scalar matrix identity. Or in other words, for any number C, if you multiply C times 1, you get back C. The identity matrix generalizes this idea in the context of matrices. So imagine that you have a matrix that's an n by m matrix, and if you multiply it on the left by the n-dimensional identity, you get back the matrix A. Similarly, if you multiply A on the right by the m-dimensional identity, you again get back the matrix A. Here's an example of the matrix identity in the three-dimensional setting. This is the 3x3 identity. And more generally, identity matrices are always square, with 1s on the diagonal entries and 0s elsewhere. Next, let's talk about the inverse matrix. And again, this idea is similar to what happens in the scalar setting. In the scalar setting, for any non-zero number C, 1 divided by C is the scalar inverse. Or in other words, C times 1 over C gives us 1. Something similar happens in the matrix then. And the idea here is that multiplying a matrix by its inverse results in the identity matrix. So imagine we have an n by n matrix A, and A to the negative 1 denotes its inverse, when it exists, and the inverse doesn't always exist. But when it does exist, A times A inverse equals A inverse times A, and both of those equal the identity matrix. And it's important to note that only a square matrix, i.e. those with the same number of rows and columns, can have an inverse. Finally, let's talk about Euclidean norms for vectors. And again, this is a generalization of absolute value in the scalar setting. So in the scalar setting, the absolute value equals the magnitude of length of a number. Similarly, vector norms generalize this idea for vectors. And the Euclidean norm can be defined as taking each component of the vector, squaring it, taking the sum of these squares, and taking the square root. And when n equals 1, or when we have a one-dimensional vector, the Euclidean norm equals the absolute value. Moreover, the Euclidean norm is related to the scalar product, in that the scalar product of a vector times itself equals the square of the Euclidean norm.
Okay, that's the Pythagorean theorem in 2D. Okay, I couldn't have done it faster than him, okay? So we kind of have a lot of this basic, it's like what, 200 level linear algebra, Don? What do the engineers do here? All these notions.
Probably.
Okay, so, oh my goodness, what's going on? Sorry. Yeah, so this is so let's before Fika, let me just breeze you through Breeze. So this is the basic linear algebra library, right? So we're going to import it, and I'm just going to sort of let's create this matrix in Amit's video. Right, I'm just basically writing things down. So you have dense matrices and sparse matrices. So if you just say a dense matrix, so it'll create this, and it's doing automatic type inference. That's a type int. You can ask what's the size of A. So size of A is simply the number of entries in A. How many rows it has? It's 2 rows, 3 columns. So you have to take the size and divide by the rows, or just say A dot columns. Now let's access the A11th element, right? So that's it's indexed from 0. So you have to do A00 of 0, 0. So here are some gotchas in Breeze. So indices in Breeze start at 0, right, as a numpy, and not like MATLAB, which starts at 1. So just be careful about it. So now I'm creating a mutable dense matrix B. And then, so now I can change the entries, of course, you know. So that's just val and var of dense matrices. And I'm just basically trying to do this step by step. So if you just play the same, you know, here's my dense vector. I can have my same vector in the video, and I can say what is its size, what's the second element, and then I can also have type infer to be double, specify the actual type, and then I can put in, remember, like before, integer looking things, but it'll still be treated as a double. I can have A as my dense vector this way as well by specifically putting 0.0 or 0.0. Now I can create a dense vector of zeros of type double with 5 entries like that. So it's a very useful thing to create. And to create, to get our fingers dirty on transpose, so we have A as a dense matrix of ints, and we do A dot lowercase t, it immediately gives us the transpose of A. And we can get the dense vector, and its transpose will be now a column 1. Okay. So here is addition and subtraction. Remember, these are element-wise. So let's create, again, A as our dense matrix and B as negative A. Right? So now we can do A plus B, which should be 0. Of course, we can also do A minus B, which will be twice A, and B minus A should be minus 2A, as we expect because of element-wise operations. So here is a little table of you know, operations, if you're familiar. So Breeze is what we're trying to get into now. This is NumPy for the Pythonista. So we will use NumPy for the foundations course anyway, but MATLAB, the proprietary one that a lot of engineers all over the world are addicted to, you know, that's the syntax, right? So here's element-wise multiplication syntax and so on. So this I always look back at because I constantly forget what syntax I'm in. So what's this pop quiz? What is a natural geometric interpretation of scalar multiplication of a vector or a matrix? And what about vector matrix multiplication? Oh, I already did this. I mean, this is what I think of. I don't know, it's how I learned in India in 8th grade. So basically having vectors as rubber bands and stretching them and actually seeing addition as the diagonal of the parallelogram. You can move that to 3D and you can iterate it to multiple D by projecting in the right planes 2 at a time. So that's what I meant here. I already talked about it, so let's not get into that. So, and then here is my dense matrix A, 5 times A, A times 5, so the order shouldn't matter. Here is dot product. So we have A as a dense matrix and B as a dense matrix. So then we can do this element-wise multiplication, you know, the dimensions of A and B must match. This is this weird star colon star thing. And then this is matrix vector multiplication. This is kind of what we will use to get at the you know, the state probability vector of a Markov chain. So here's my dense vector A, lowercase a. So this is 2, and I can do A times A, and I get my dense vector minus 3, 2. Is that right? Yes. Yeah. 1 minus 4 is minus 3, so it's good. So here is matrix multiplication. There's my A and B and A times B. Okay, so this is just yeah, so I'm just manually checking the first entry of A times B should be 46 here. Identity matrix, so we just say A is the dense matrix, and then I can do dot EYI of type int of 3, so then it gives me the 3 by 3 integer typed identity matrix. And then I can just do A multiplied by the identity is A itself, identity multiplied by A is A itself. Inverse is a pretty non-trivial concept, right? Because you need notions of volumes of objects and or determinant, this weird thing. But anyway, it's yeah, it's an elegant concept in linear algebra. So basically, you have a dense matrix, and I can just find out what its inverse is. Of course, the inverse is if it's well defined. You know, for a square matrix with m and n, number of rows and columns the same, then I multiply d by its inverse, I get the identity, or inverse by d, and I get the identity. Right? So yeah, finally we just have the Euclidean distance and the norm. These are the absolute minimum you need to like start understanding things like recommender systems or any kind of iterative dynamical systems, by which I actually am talking about optimization algorithms. They're all like some kind of heuristic dynamical systems that are doing something, right? So these are the most basic operations we need from this MITS video. Okay, so of course it makes sense. So here is a bit more pointers before Fika. So I already pointed out this quick start, Scala NLP Breeze library. And yeah, this was just a markdown from that library. So it's pretty much everything. Here is some other things you can do, you know, more clever so-called broadcasting, like what MATLAB tries to do, so you can do a lot of operations in parallel. So I'll let you guys look at that, and then we can do some visualizations in Breeze. People are very peculiar about the visualization tools they already know, so I won't really, but it has a visualization library. These are things I'm going to let you watch later because we won't have time to keep watching videos. So this is on elements of big O notation and space and time complexity, something you learn in a second semester computer science course. Like, you know, because we want to track how well our algorithms are doing. So this is about that type of basic stuff. And it's Fika time. So when we come back, we'll get into linear regression in Scala. And then I'll sort of do some simulation of simulation data, and we'll try and fit a plane to a bunch of data. And then I'll drop into distributed linear algebra. A lot of this I'll kind of skim through depending on time. And in the worst case, we'll do graph frames tomorrow, right? I don't want to over rush either because you really want to, yeah. So let's play it by ear. So we'll start again at 3:30.
There is a small gotcha.
Oh, is there a what did I do? Is there wrong? Something wrong?
No. You didn't do anything wrong.
Yeah.
There is a gotcha in Breeze that I ran into.
Oh, what is that?
So Breeze supports complex numbers. So you can use complex numbers, add, do whatever you want with it, use them in matrices and whatever.
Yeah.
But it doesn't support all matrix operations
on
matrices with complex numbers.
Oh, right.
So for example, you can't take the inverse of a complex matrix.
Yeah.
In Breeze.
Uh-huh. But does it say, I'm sorry, I can't give you, or does it just spit something at you?
Well, it has to do with Scala tells you that there's no implicit for doing inverses of complex matrices.
Okay.
The explanation from the developers is that they haven't found a good way to well, I mean, the back end they're using is LAPAC, right?
Okay.
And they haven't found a good way to unbox complex numbers and send LAPAC using the current API.
Yeah. And LAPAC is still mostly Fortran, or?
I think so, yeah.
Yeah. Actually, all this distributed linear algebra, way under the hood, is 1970s Fortran code. So a lot has